To a new lecture. In this lecture, we are going to describe the elements of vector algebra because we already saw that a scalar quantity is adequately given by a magnitude. While a vector quantity requires the additional specification of a direction. So the basic algebraic operations for handling of scalar quantities are those familiar ones studied in junior classes. But for vector quantities, these methods may be cumbersome since the directional aspects must be taken into account. Therefore, an algebra has evolved that clearly and concisely allows for certain very useful manipulation of vectors. So, first of them is what do you mean by magnitude of a vector? The first thing I would like to tell you something about magnitude of a vector. What is this? Basically, the magnitude of a quantity in a strict mathematical parlance is always a positive number of units, whose value corresponds to the numerical measure of the quantity. Suppose that the magnitude of a quantity of under consideration is minus 50 units. It may be anything, maybe temperature minus 50. But what will be its magnitude? You have to notice one thing, that the magnitude of a quantity is its absolute value. And the mathematical symbol for indicating the magnitude of a quantity is a set of vertical lines including the quantity, that you can write here simply the magnitude of the measure minus 50 units. Simply you can write like this, and this should be read as absolute value of minus 50. So absolute value of minus 50 units, and this will come out as simply as plus 50 units. So similarly, in the same manner, the magnitude of a vector quantity is a positive number of units corresponding to the length of the vector in those units. So using our vector symbols, we can say that magnitude, suppose we want to write the magnitude of a vector A. So what will be it like? If you want to write magnitude of vector A, like this, then you should write it like this, and it will come out something like length of that vector, and this is always a positive scalar quantity. So now I would like to discuss the multiplication of a vector by a scalar. Multiplication of a vector, suppose that vector A by a scalar, and a scalar I will prefer it writing M, and this is nothing but multiplication on when a vector A is multiplied by a scalar M. It can be simply written as M multiplied by vector A. And what is this MA? M multiplied by vector A. A vector multiplied by a scalar. What is it? It is a vector basically. MA is a vector having same direction as vector A and magnitude equal to the ordinary scalar product between the magnitudes of m and a. So you can write that magnitude of vector a is simply this thing. If if m is positive, then you can simply write here ma, but I'm not going to write this because if m is negative, it means simply that the vector ma has a direction directly opposite to vector a. That means if you got a vector a like this, and if you have multiplied it by a scalar m, and m is negative, that means I don't know exactly the magnitude because it will depend on the absolute value of m. But if m is negative, ma is going to be directly opposite to that of vector a, and so the vector minus a may be considered the vector minus a should be considered as the product of the scalar -1 multiplied by vector a. It should be considered like this. And as I said earlier, that minus a differs from minus vector a differs from vector a in that it has an opposite sense. And these operations have nothing to do with the line of action of a vector. So vector a and minus vector a have different lines of actions, they may have, and but their directions must be opposite, and of course their magnitudes are going to be same, their lengths should be same, because the magnitude of minus vector a and magnitude of vector a, they are going to be the same. No problem, but their directions must be opposite. So negative of a vector means nothing. This is a scalar multiple of vector, and in this way we define the negative of a vector, nothing else. And now if you like to discuss the addition and subtraction of vectors, that is what is called addition and subtraction of vectors. Subtraction is basically if you want to add two vectors a plus b, well, it is a plus b. But if you want to find a vector a minus vector b, you should always think it like this is a plus minus vector b. Minus vector b is opposite to vector b in direction wise. That minus vector b has a direction opposite to that of vector b, and they must be added. Subtraction is also an addition in vectors. So that is why I told earlier that addition and multiplications are defined for vectors, not the subtraction. But this thing, and by tradition, by habit, and they must be taught and work like a subtraction procedure. So, and to do vector addition, we generally use two methods. One method is force, based on force, that is when you say there are two forces A and B acting on a single point, that means their tails are joined. Then in case you want to find the sum of these two vectors, you have to complete a parallelogram considering both the vectors as bases, and you will get a unique diagonal that also emanates from the tails of vector a and vector b, and this will give you vector a plus vector b. And obviously you can see here that vector a plus vector b, length of vector a plus vector b is certainly not a plus b. It cannot be possible. before you degenerate your parallelogram, you can't write like this, so you have to be careful, a bit careful here. And then how can we find the length of vector a plus b? Go through the uh, trigonometry lectures, and we have described law of sines and law of cosines. If you don't remember, I can again explain it, that if we have a triangle, side length a, b and c, angles as alpha, beta and gamma, you can write here something like law of cosines permit you to write a relation like b square equals a square plus c square minus 2ac cos beta, like this. That means you can write cos beta equals a square plus c square minus b square divided upon 2ac. And law of sines, sine law also permit you to write a by sine alpha equal to b by sine beta equals c by sine gamma, and like this. And you can use these results to find out the lengths of the vectors whenever you needed to do so. Nothing else is required. You can use these results always. And when we did this, we have a vector a, another we have vector b, and we completed a parallelogram and got our vector a plus b. We can also think it like if we make this also an arrow, a direct line segment or a vector, if we try to make this side of the parallelogram also a vector, it will have the length of vector b and direction same as, because these two lines are parallel, so it will also have the direction of vector b. So from the equality criteria of two vectors, this vector can also be written as b, and in the similar manner this vector can also be written as vector a. And then you can find out any of the triangles, because we have two visible triangles here. First triangle, I'm going to redraw it as this one is vector a and this one is vector b, and we got a vector a plus b like this. These methods are called triangle law. This diagram is called simply called the triangle law, in which we put the tail of another vector on the head of the first vector and join the first vector tail to the next vector head, and we will get this is also called the head tail method, and we get a triangle if the angle between vector a and vector b is theta. You can see here is also the angle between a and b is theta, and you can use your law sine rule or cosine rule to find the lengths of triangles. And you can see here that you just consider this triangle. You can consider another triangle that is like this. This is vector b and this is vector a, and you got again this is a plus b. That means you can be sure that a plus b is equal to b plus a here. Both are same. That means they obey the commutative law. That means they can commute. The law of the ordering doesn't matter here. So You can see one more thing, that this vector addition also obeys the associative law. That means you can write a plus b plus c is equal to a plus b plus c as well. There's nothing special about it. वैसे तो मैं प्रोवाइड कर सकता हूँ, आई कैन प्रोवाइड यू सम insights. I don't know whether it will be useful or not, but I'm trying to do so. I'm trying to make you this associative law visible. Let me have two vectors, like this is vector A, this is some kind of vector B, and here we have a vector C. Or let me draw another picture for it. This is our vector A, this is vector B, and this is our vector C. Then if we try to find out first vector B plus vector C, just complete the parallelogram and you will get here vector B plus vector C. Now add them with add vector B plus C to vector A, and to do so we will again need to complete the parallelogram. I hope it looks good, and this vector will be simply A plus B plus C. And if you again draw all the pictures, or if you draw all the pictures again, look, this is your vector B A, this is your vector B, and this is your vector C. Now first try to find out A plus B first. So to find A plus B, I will complete this parallelogram, and this is going to be A plus B. And now we are going to add A plus B and vector C. So let me draw another parallelogram like this, and this is now A plus B plus vector C. And if you compare both these pictures, you will get perhaps convinced that vector addition obeys the associative law. And it is true, we don't have a graph paper, and we are not making accurate calculations here, but I'm just trying to show you that associative law is also valid. And I can show you one more thing, like if we have vectors like three vectors like F1, like F2, and another vector as F3, and if we try to find out F1 plus F2 plus F3 like this, I can draw another picture, like F1 is here, and then I put F2 like this. They are all rough sketching, and then I can draw the F3 like this. F3 like this. This is going to be F1 plus F2 plus F3. And if I do same thing, like I first take the F2 like this, and then I add it with f3. f3 is like this, and then I can draw f1 like this. We will again get f1 plus f2 plus f3, or f2 plus f3 plus f1 is again like f1 plus f2 plus f3. These are rough sketches. Clearly, the order of laying of the vectors is not significant. You can add a plus b plus, you can find a plus vector b plus vector c by simply adding vector c plus vector b plus vector a, or vector b plus vector a plus vector c, like this. The order of laying of the vectors is insignificant, not significant at all. These are things you need to consider in vector addition. What is a vector subtraction? In fact, it is nothing. It is something like you want to add two vectors, like this one is vector A and this one is vector B, and you need to find vector A minus vector B, and that is of course A plus minus B. So just draw your minus B. Minus B will be like this, of the same length but in opposite direction. This is minus B, and complete your parallelogram, and this is your A minus B. So A minus B is like finding A plus minus B. So the process of subtraction is defined like to subtract vector B. But if you want to subtract vector B from vector A, you need to reverse the direction of vector B and then add this with vector A. And I think these things are simple. In the next video, I would like to try the resolution of vectors and its scalar components. So thank you very much for now.